We are going to draw curved arrows to show how products are formed in the acid-base reaction shown below. Here we have a reaction between a terminal alkyne and sodium ethoxide. So we are going to first draw our charges on sodium ethoxide, which is NaOEt. Na is plus, so Na plus, and OEt is oxygen is minus. There are 3 lone pairs on the oxygen, and it's always a good idea to write it in as complete Lewis dot structures so you can draw your arrows properly. Once you have drawn the Lewis dot structure, the next thing is to determine which of these compounds will act as the acid and which one will be the base. Sodium ethoxide would be the base in this reaction, and the alkyne will be the acid. Since the alkyne has different types of hydrogens, we are going to decide which one is the most acidic proton in the alkyne. The most acidic proton in the alkyne is attached to the sp carbon of the alkyne. Once we have picked our acid and the most acidic proton in the acid, and we know what is the base, we are going to draw the curved arrows to show the proton transfer reaction. Arrows always move from the base. The lone pairs, the electrons grab the most acidic hydrogen, and the CH bond breaks and moves on top of the carbon. Once you have drawn the arrows or the curved arrows, you're going to draw the conjugate acid and the base formed in the reaction. The conjugate base that's formed from the terminal alkyne should have 5 carbons. You have 5 carbons in your starting material. Always count your carbons. And is the salt of the alkyne. The sodium ion associates itself with the conjugate base. The ethoxide ion, OEt minus, grabs a hydrogen, so it would form ethanol. Which you can also write as Et. Which you could write as ETOH. So you now have the conjugate base and the conjugate acids, which are the products of this acid-base reaction. The last thing to do is to determine the direction of equilibrium. To find the direction of equilibrium, we look at the pKs of the 2 acids that are formed in the reaction. One is your starting acid, which is the alkyne. The pK of alkynes are listed here below in the pK table. Terminal alkynes have a pK of around 25. And the conjugate acid is alcohol, ethanol. Listed here is a pK of 15.9. Acid-base equilibrium moves towards the weak acid. Weak acids have a higher pK. So when you compare between the terminal alkyne and ethanol, you see that the starting alkyne is the weaker acid. So equilibrium will move towards the weak acid, which is represented by arrow D. the equilibrium is moving backward, that means this reaction really doesn't work, which basically means sodium ethoxide OET minus is not a strong base and is not able to deprotonate the terminal alkyne. The stronger base in this reaction is the conjugate base that you had formed, which means that the backward reaction will move because the salt of the alkyne will grab a hydrogen from ethanol and move the reaction to the starting materials. So to summarize, we had a reaction between a terminal alkyne and sodium ethoxide. The conjugate base is the salt of the alkyne. However, the conjugate acid formed in the reaction, ethanol, is stronger acid than the starting alkyne, which basically means that the equilibrium will move backward. The reaction will not work in real life. Sodium ethoxide is not a strong base enough to deprotonate the terminal alkyne. Other bases that you could choose would be sodium hydride, NaH, which would give hydrogen gas, move the equilibrium forward, or NaNH2, which would give you an ammonia, which would move the equilibrium forward, or other bases that would generate much strong, weaker acid. You could use R minus, beta lithium, which would also work.